Hello everyone. Today our group project gonna present the topic about the solar rooftop project for Wat Suthiwararam School. So this is our group member and we have project advisor as Assistant Professor Komsan Hongsongbat and our project committee as Dr. Nichapenya Shanda Nashulaga Loikrai. The overview, we start off with introduction followed by objective and gonna mention about the scope of work, followed by theory and including the material, mentioning about methodology, and end up with conclusion and suggestion. For introductions, in the realm of investments, offering alternative opportunity is vital for mutual benefits, particularly amid contemporary challenges like fluctuating energy costs affecting educational institutions. Integrating solar power emerged as a practical solution, promising economic and environmental advantages. This study concentrated on the tangible effects on solar installations at Suthiwararam School, employing PVCs for thorough financial analysis. The findings highlight potential cost saving, underlining the significance of solar integrations in school for both financial stability and environmental sustainability. Our objective, we aim to assess the feasibility and internal rates of return, so-called IRR, of implementing solar panel at Suthiwararam School in Thailand, using PVC software for analysis. The study compare outcome when solar panels are affected by shadow and non-shadow conditions, highlighting significant changes. We seek to make informed decisions about investment opportunity by understanding various financial aspects and parameters that relevant to the field, such as NPV, IRR, and interest rate.
Scope of work: study of software that correspond for solar computation including PVCs, understanding the shadow scenario and know how to construct the result and compare, and analyze the output result obtained from the software in aspects of economic from investor and customer.
The theory for our project, we have three main of them, including economic, environment, and solar panels. Now, let's clarify these three terms for economics. Let's start off with NPV. NPV is stand for net present values, where we compute the formula to evaluate how much benefit would the investor will gain for the given years. IRR is stand for internal rate of return, where this parameters is determinations of time durations to return the lost investment to become zero or positive profit on that year before starting to gain absolutely consistently a profit afterward. And finally, the interest rate. In additional percentage that you have to defray all the outlay that you load from the bank, aside from refund of the initial outlay. This is for the case where you loan money from the bank, you have to return afterward. This is the table chart of financial interest. We set interest rate at 5%, the outlay rate at 20 Thai baht per watt peak. And MKT rate is similar to the outlay. We set it as 1 Thai baht per watt peak. What is watt peak? It is the power in DC forms. What is MKT? MKT is similar to the commission rate where you hiring someone to install a solar panel on rooftop. In a section of environment for the shadow, shadow on the solar panel affect the loss caused by electrical energy, which is greatly reduced when shadow fall on the solar panels and cause heat to accumulate in the cell, of course. So this is simple shadows parameters. So this is a quick overview for elevation angles. For all type of angular angle, we have altitude angle, zenith angles, and azimuth angle. Third topic is the PR laws, and from that image, we have 8 types of the PR laws. PR is stand for performance rate. So we have the shading loss lost by the shadow from other object, the dust loss where the dust cover on the solar PV, which is possible. The thermal loss is just the overheat that caused more resistivity along the wire or some kind of load. We have solar inverter loss, the solar panel mismatch loss, the DC cable and AC cable, whereas work similar to each other because the more heat, the more resistivity, and finally the low radiation loss. For the theory of solar panel, we have the type of solar panels, the components. So there are three main types of solar panel. First, we have monocrystalline, the most efficient solar cell, but most expensive. It's used only for small area. Second is polycrystalline. It's less efficient but affordable, used for the medium areas. Thin films are less efficient than both mono and polycrystalline, so they are more often used in industrial solar installation, in which space is not a problem. So, so this is a quick overview for components. We have solar cells, solar glass, EVA, black sheet, aluminum frames, and junction box.
From software, we use PVSys program to analyze a suitable for requirement load on a building and Excel program to analyze how worth for the investor to accept the deal. For hardware, we use laptop to gather data from internet and website. We use kilowatt inverter in this project because it offers a variety of high-performing solar batteries and inverters at a fair price. For solar panel, we use Astro Energy 565 watt bifacial in-type. Our methodology: first, find a reference location and generate the system. Display how much solar array should be installed based on average annual tariff. On the second, read all requirement data from the report, including solar panel, inverter, all the components required to deploy along the system. In addition, we have to take parameter both unit kilowatt hour and DC input in kilowatt peak. And the last one, analyze the load and turn AC to DC power before put in PVSys. Afterward, plug in parameter from the PVSys report, then analyze the IRR for investor and how much could customer save compare between shadow and non-shadow simulator.
Alright, once you get the DC power from the previous Excel, we simply go on the PivotSys program and click it on Grid Connections. After that, we set up the name of our project that we are working on. Followed by clicking on this one, we simply go on Google Map and find the place that we are working on and simply copy their coordinations and placing the coordination along the programs in order to allow the pivots to find exactly the right spot that relates or correlates to the actual orientation of the suns. And after that, we set up the tilt angle for our solar panels. Now, we go on the system in order to place the DC power that we got from Excel to calculate for the proper array such as the module string and series solar panels. Also, it is calculate for the proper size of inverter as well. Our project, we do it in 25 years, so we set as 25 in order to find the loss. This is the performance ratio. So this map is not like the previous map because we go on Google Earth Pro to copy the image of the map for working on the shadow. So we save the image and for the image along the shadow system of the pivot system. And we select the single PV tables in order to come up with the solar panels. And how we decide the PV panel, we have to look on the design of the array. In this case, we're working on the series. Let's say that instead of 18, we have 10 series. So we have to design how the solar cell in order to have completely 10 series. For me, just using the method of 2 by 5 block in order to contain 10 series. Now, we generate the solar panel of one set. And now we have the 12 string. So each strings contain 10 series of solar cells. So one set had 10 series, 12 strings has around 120 series. So we come up with 12 sets, placing on the rooftop. And then we generate the shadow analysis in order to see how the shadow works by simulating the movement of the suns. As you can see on this picture, the shadow hit the small building. And if you can run the shadows, you will see this chart, which is identified that which orientation would be appearing of the shadow. And this is the single line diagram of three solar rooftop. So M1 to M3 is represented as the load. And once you've done all this step, we simply generate the report by run the simulations. It's how the report would look like once you're done running it. So we name it as suthiwararam with, let's say, 151 kilowatt peaks. So the report would be like this. PV array characteristic tell us all the information that we do require. This chart, we're gonna look only at the PR loss, which is the part that we're gonna put it on the Excel for the next step. So as you can see, we working on this project for 25 years, so the loss could be degraded to the 17.3% for 25 years, and it start getting decay as we use consistently over year and over again. This line curve graph tells us of the total of energy that could be generated by the solar panels. The orange one on the top, it is the total energy that could possibly produce with 100% without considering the loss. But for our project, we're gonna take P75, which is simply means that it has loss for 25%. P75 is 92.06 megawatt hours. So we take this as the values in order to plug it in on the Excel. Once you have PVSys reporting, we move on to the Excel. This table we call it as feasibility tables. On the most left side, it is the percentage of electrical or tariff charge being increased by 2% in every single years. We also have the total energy that generated by the solar panels. We also have the loss percentage of the energy over 25 years as well. And of course, we have to consider FT charge as well. And the most important thing is the rate circle above the chart. Our example, let's say we have the report that says that we have 148 kilowatt peaks. So we simply use this value and plug it in on the above chart that we just circle. Let's discuss a little bit about financial aspect. This part of Excel allow us to have a look of how we can find the defray that have to return the bank payments. We look at the formula. The defray for each year represent as defray N, resulting of outlay in or outlay from that year subtracted by initial outlay divided by 7 because we're gonna pay the bank within the range of 7 years, followed by adding the outlay of this year as well, but multiplied by 5% as an interest rate. So we got the defray for each year. Now we're gonna find the total defray. According to the equation, total defray is start from first defray where there's still no subtraction of outlay or interest rate, followed by adding the sigma 7 2 because we start from year 2 to 7, followed by outlay n minus because we're gonna count the previous outlay values subtracted by the previous defray as well. Also, we subtract with the outlay divided by 7 because we do it in 7 years and adding with outlay in this year times interest rate. Similar to the previous equations, we do it consistently until we reach year 7 and we're gonna got the final result of the total defray that we have to subtract out of the profit in order to get the actual one. Aside from the loss of the total payment for the bank, we also consider the loss of the maintenance, which depend on our policy. And our policy state that we have to pay for the loss of maintenance in the range of 15 years by simply use this formula 0.2 multiplied by what peaks in order to get exactly the charge that we have to pay on the maintenance within the range of 15 years. And the next one is the tariff charge that we taking from our customer. And in order to know how much do we have to take, we're using the revenue meters in order to determine how much that we can get from our customer. And same, we do it in 15 years according to our policy. And from our policy state that first 15 years, we're gonna take around 80% of all tariff charge from the customer. Therefore, customer gonna save just only 20% of the tariff within a range of 15 years. However, they don't have to pay for the maintenance cost as a return. So this formula, we take it from the previous formula that we just mentioned about the policy. Now we're gonna concern more about the tariff charge of how we can get this kind of formulas. Start off by looking at on peak and off peak. Why do we get 4.2 and 2.6? Well, we start from that. We summation of all three load in the form of DC and converting back to AC in order to tell how much would the charge requiring. If it is more than 30 kilowatts but still less than 99 kilowatts, well, it would be considered as the medium general service. So all we consider is an energy from the general service charge formula, which includes on peak, of course, of peak and FT charge, and 0.65 for on peak and 0.35 for off peak is the ratio of the total day in a year that determine how many days that are satisfy the on peak and another total day that satisfy the off peak, which is weekend, holiday, something like that. Moreover, the reason we divide the multiply by 1.02 is because every year the electrical charge will raise by 2%. So the formula is going to look like this. From this table, it is represented in the perspective of the customer. According to the policy, in 15 years, that customer will only receive 20% discount of the tariff charge. So in the range of 15 years, customer will save less comparing with the rest of 10 years. As you can see, the first 15 years is around 100,000 baht, while from the rest of 10 years, customer will save for around 600 to 700,000 baht, which is quite a lot of change. While customer can save a lot during the last 10 years, customer have to pay a little bit amount of maintenance costs. But according to the policy, customer have to pay twice as investor. So as you can see right here, customer has to pay by equation of zero point 0.4 multiplied by what peak, and you get the result the customer had to pay for the maintenance, but still didn't change that much. So that's how it works for the customer. From this table, as a result, customer will save around 9 millions for 25 years. So this is the final result of financial tables. It is summarized of how much investor would make the profit and how much customer would save the bucks. So this is the comparison between the non-shadow scenario and the shadow scenario. We know the NPV of the investor. So what we have to do, we have to find IRR in order to determine whether this project it is worth for investment. We use the formula from the Excel as IRR in the bracket in order to find the percentage of it.
In conclusion, the comparison between shadow and non-shadow scenarios highlights significant difference for investors. Shadows from nearby buildings reduce annual energy generation by 25%, resulting in about 8 million Thai baht in lost revenue. The project's internal rate of return, or IRR, indicates a 7-year recovery period in the shadow scenario. In contrast, customers save around 17,347,694.37 Thai baht over 25 years in the shadow scenario, two-thirds of the non-shadow savings, which means 26 million Thai baht. The specific shadow computation program ensures maximum light exposure, making the agreement acceptable. This emphasized the importance of a comprehensive environmental analysis in solar energy investments. From our given scenario is already included interest payment, which simply means that if interest payment are negligible, IRR and NPV will be increased. For suggestion, 1. Find a kilowatt peak for the solar cell. Before computing the PV6 reading electrical bill, it's very crucial to look at the given unit along the bill carefully to prevent getting the wrong value. 2. Shadow analysis. We have to compare which part of the building is facing toward north direction to make the exact same part of the image map on program to be fading the same as usual. 3. IRR. There's no fixed at IRR cost, whether it is worth for invest, since investor has different perspectives, so to indicate we must understand the investor view toward the investment. And thank you for watching our presentation.